I welcome you all for engage your learning experience with pantechelearning anytime, anywhere, at any places. We are always supporting to the students in a technical way, and our main vision to help the 10 million students easily learn the technology. So today we are going to discuss about one interesting topic. So what is the topic? We are going to tracking the pedestrians from a moving car. So we are going to discuss about an interesting topic, that is a tracking pedestrians from a moving car using a camera. So here we are using the camera. So that camera mounted on a ego car watching the surroundings. We are going to learn how the camera in the car can spot the people walking around the vehicle. So even when the car is moving also. Since the car is moving, the people in the video are moving too. So we need to make sure we keep on track of them from frame to frame. So that is why we are going to create one program about this. So for this, I'm going to open the MATLAB software. So before we get into that, first I'm going to tell you the process of this automatic detection and tracking of a people from a moving car. So what are the steps we use? First, we have to detect the people. So the first step, the main step, is to detect the people in the video frames that captured by the moving cars camera. So this is typically done by using the CV algorithms or such as the deep learning based object detections, YOLO algorithm like that. So these models are trained on a large data sets that containing the images of the pedestrians and that can accurately identify them in the video frame. So second step is the customized non-maximum suppression. So what is this? Once people are detected in that video frames, it's a common to have any overlapping detections or any multiple detections for the same person. So to address this is one kind of the technique that is called non-maximum suppression is applied. So in this case, the customized non-maximum suppression may be necessary to adapt the challenges posted by a moving camera. So the next step is motion-based tracking. So with the accurate detection of the people in each frame, the next step is to track their movements over the time. So this involves detections across the consecutive frames to form the tracks that representing the trajectories of the individual pedestrian. So the first one is the people detection and second one is the non-maximum suppression and third one is the motion-based tracking. So here I will not change that one. So the third step is motion-based tracking. So next we are going to get into that program. So for that I'm going to open a MATLAB software here. Yeah. So first, so this is our program. That's a pedestrian tracking moving car. And here I'm going to, first we are going to use the main function. So this is the main function, that is a pedestrian tracking moving camera. It likely contains overall logic and flow of the pedestrian tracking algorithm. The first line, so we have to create the first line. So this is the first line function. This line, it defines the start of a MATLAB function. What is the name here? Pedestrian tracking moving camera example. So this functions in a MATLAB, it consists of the code that performs some specific task that can be called from the other parts of the program. So that is why we are going to define by using the define function. So next we are going to create the objects that is used for reading the video. So this is the object. So what are the file we have used? These lines, it defines the two variable. One is the video file, another one is the scale data file. So which stores the path to the video file containing the footage from the moving camera and also the data file that containing the scale information for the pedestrian. So that is why we are going to create this file, video file. Another one is the scale data file. Next we are going to create the object here. So this line, it calls a function named setup system objects with the two arguments. One is the video file, another one is the scalar data file. So and assign output to the variable named object. So this is a new variable name, that is the object. Next one, so mainly this function is responsible for the setting up a system objects for reading the video and loading the necessary data files for that video. So that is why we do that one. And we are going to create a detector. So this line, it initializes a pedestrian detector using the ACF. So ACF in the sense aggregate channel futures, and this is one kind of the method. So this method is specifically trained for the detecting the pedestrians. So here we are using the one argument, that is the call text. So this call text argument, it specifies the data set on which the detector was trained. So next we have to create an empty of tracks. So this line, it calls a function named initialize tracks to create an empty array named track. So this array will be used to store the information about the each detected pedestrian track. So next we mention the next ID equal 1. So this initializes a new variable name. So that is the next ID. The value is a 1. So this variable will be used to assign the unique identifiers to each pedestrian track. So next we are going to set the global parameters here. So this is the global parameters. So ROI and gating threshold value and cost of non-assignment value should be 10 and time window size should be 16, like that. So these lines, it define the various parameters that is used in the pedestrian tracking algorithm. That is the region of interest, thresholds for the gating and confidence and visibility. So this entire loop is to process each frame of the video. So now we are going to take another one. So that is the detected people and track them across the video frame. So this is the stop frame. We mentioned the stop frame is a 1629. So since in this loop, it involves multiple steps. So now I am going to create the auxiliary input and global parameters for the tracking system. And we mentioned here, this is the auxiliary input. So what are this inputs only we call before that this one. So before this the ROI and also the confidence test. So now I am going to here. So this auxiliary input in the sense that is the, what is it? Just a minute. Yeah. So this auxiliary input is a PED scale table. So this is one kind of the vector that contains the information that is relating the pixel location in that image to the size of the bounding box marking in a pedestrian location. So each entry in this vector, it represents the estimated height of an adult person in the pictures. So next we specify the global parameters also. So what are the global parameters we use here? So region of interest, yeah. So this is the region of interest. So it specifies the processing area in that image. And next one is the SC threshold. So this is the scale threshold. So it controls the tolerance for the scale estimation. And next one is the gating threshold. So it determines the maximum acceptable cost for exactly matching the detected and predicted bounding boxes. So next one is the gating cost. What is this gating cost? This value is used in the assignment. So we used in this program, that is the cost matrix to discourage the certain tracking to the deduction assignments. So next one is the cost of non-assignment, and this one, it controls creating a new track when no association is made between the detection and track. So these are the global parameters. So these parameters plays a very crucial roles in this tracking system by controlling the various aspects such as the detection accuracy and track creation and track maintenance. So that is why we create this one. So next, I am going to create a system object for exactly tracking the system. So I am going to set up the function here. So that is why we use that function dot object. So this function, it sets up the system object that initializes the system objects recovered for the tracking system. Now we are going to initialize a new command. So that is the overview purpose. I am going to here use that initialize video output, and we have to create a video file. So this one, it creates a video reader object named object.reader. So this is the object name. This is the variable name to to read the video frames in a specified video file. So next we create a vision.video player object. What is that vision.video player object? A variable name, that is the object.video player. So here we using this function vision.video player. So inside we mention to display the video frames by using the position. So this position parameters, it specifies the position and size of the video player window. So next I am going to, just a minute, next I am going to load the scale data file. So this line, it loads a scale data file specified by the scale data file. So the load function is used to load only the PED scale table. So that is why we mentioned that. So this is one kind of the variable from that file into the structure ID. So this is a new variable. So this PED scale tab is assigned to the object.PED scale table property. So that making it accessible within that object.id. So overall this function, it sets up some necessary components for exactly tracking the system and including the video reading and video display and loading the scale data for the pedestrian detection and also the tracking. So that is why we create that one. So now I am going to initialize the task. I am going to initialize the track. So this initialize track function, it creates a one kind of the array of the track. So each representing a moving object such as the pedestrian in the video that being analyzed by using this initialize tracks. So for that we are going to set up that one. So here we are going to create this line, it creates the initialize tracks which initializes the array of the tracks. So next one, what is it next one? So inside this track we mention, we call these or all the, what is it? This block, it initializes the empty array tracks where each element is a structure representing a tag. So each track structure that containing the following fields. So what are the fields? ID and which color and bounding boxes and scores and Kalman filter and also the age and total visible count. So ID in the sense, what is this ID? So it's one kind of the integer ID that is assigned to that particular track. Next one is the color. So this color it assigned to the track for the display purpose. And next one is the bounding box. So what is the bounding box? It's one kind of the matrix that representing the bounding boxes of the object. So where each row that is corresponding to the bounding boxes. So next one is the scores. So it's one kind of the vector that's storing the classification scores from the pedestrian detector. And next one is the Kalman filter. So here we mention the Kalman filter. So this Kalman filter object, what is the purpose here? So we use this Kalman filter object for a motion based tracking and typically tracking the center point of the object in that image. And again we mention the age. So this is the number of frames since the track was initialized. And next one is the total visible count. And this total number of frames in which the object was detected. That means visible. So next one is the confidence. Confidence in the sense it's a pair of the two numbers that representing the maximum and average detection scores within the predefined time window. Next one is the PRED position. So this is the predicted bounding box in the next frame. So that estimating using the Kalman filter. So we have to initialize all these fields within that track. We have to initializing the tracks with these fields. So this function, it sets up the one framework for storing and managing the state of the each tracked object. So including its position and detection scores and what is the confidence level like that. So next we are going to detect the people. For that we are going to use the function here. So inside this function detect people. So function of centroids, bounding boxes and scores. So this line it defines the detect people with no input arguments and return the three outputs. So here you can see this with no input argument, but we return the three outputs. One is the centroid, another one is the bounding boxes, another one is the scores. So centroids in the sense that is the center points, and bounding boxes and deduction scores of the detected people respectively. So next we have to resize the ratio. So this block, it resizes the input frame to increase the resolution. So that is very easy to detect the people further away from the camera. So that is why we use this resize ratio function. So next we call one line here. So that is the run ACF people detector. So this line, it runs the ACF, that is the aggregate channel futures, by using the people detector on the resized frame within that specified region of the option.roi, and also here just a minute. So this is the option.roi and number of scales and window strike and selected strongest to the false. So these parameters, it specifies the step size for the sliding window detection. So next we have to calculate the estimated height of the each detected pedestrian, that is based on the location of their feet within that boundary boxes. So here we use the pre-calibrated data, that is the object.ped scale table, to look up the estimated height based on the pixel location on the feet. So next we are using this invalid function. So this block, it removes the deductions whose size deviates from the expected size based on that calibrated scale estimation. So that means PED scale table. And next one, this is the we have to apply the non-maximum suppression here. So we discussed about the non-maximum suppression in the starting. So this line, it applies the non-maximum suppression to the select strongest bounding boxes. So here we are using the overlap threshold value. So this parameter, it specifies the minimum overlap between the bounding boxes for the suppression. So next we have to compute the centroids. So finally this block, it computes the centroids of our remaining bounding boxes, and that representing the center points of the detected pedestrians. So if no pedestrians are detected in the sense, this centroid is set to an empty array. So next we are going to predict the new locations for the existing tracks. So this function predict new locations of existing tracks. It defines a function of this one. So which is very responsible for predicting the new locations of the existing tracks. So it does not take any input argument. So here we are using the for loop, and inside this loop, it iterates over each track in the track array. So where each track represents a moving object in that video in the sense. Next we have to retrieve that one. So retrieve the lost noun bounding boxes, that is a B box, and that associated with the current track. So next we have to predict the current location of the track. So this line uses, here we use the Kalman filter, that is associated of the current track. And that is why we mentioned the tracks of I.Kalman filter. So next we have to shifting the bounding boxes. So this line, it adjusts the predicted bounding boxes position based on the predicted centroid and also the size of the noun bounding boxes. So it must ensure the center of the bounding boxes aligns with the predicted centroid, while maintaining the same width and height as the previous bounding boxes. So this function, it's effectively uses Kalman filter here to predict the new locations of the existing tracks in the current frame of that video. So that is why we use here. And now we are going to assign the deduction tracks, assign deduction to the tracks. So here we have to write the function here. So inside this function of assignments and unassigned tracks and unassigned deductions and deduction to track assignment. So this line, it defines a function which computes the assignments between the deductions and existing tracks. So it returns in three outputs. One is the assignment and unassigned track and unassigned deductions. So again, we have to compute the overlap ratio between the predicted boxes and also the detected boxes. So that is why we use that one. So inside this predicted bounding boxes, this block, it computes the cost matrix for the assignment. So where each element representing the cost of the assigning a new deduction to a track. So this cost is based on the overlap ratio between the predicted bounding boxes of the track and also the detected bounding boxes of the track. So higher overlap ratio means that is indicated as a lower cost. So next one, this is the force optimization step. So here we adjust the cost matrix to ignore the certain matches that are setting the associated cost to a largest number. So it is useful for the gating purpose. So that is why we mention here. And next we solve the assignment problem by using this condition. So this line, it solves the assignment problem using the optimization algorithm. So it is basically determines the optimal assignment of the deduction to the tracks based on the cost matrix and also the cost threshold of the non-assignment track. So this function efficiently performs the assignment of the deduction to the existing tracks and optimizing the track that is processed by the deductions with the most likely corresponding tracks while considering the cost of the assignment and also the gating threshold. So now I am going to run this simulation. So before I am going to run this simulation, I will give you the assignment details to you. Code here. So just I am going to run this code. So just a minute, it will take time. Yeah. So this is the output of that video. Just a minute. Yeah. So this is the output. So it's clearly detect all the pedestrians in this road. So moving camera. So we discussed the Kalman filtering and how to apply the Kalman filtering and how to create this scale estimation about the relationship between the pixel location and also the pedestrian size. So this information helps in estimating the size of the detected pedestrian, which is a very crucial for accurate tracking. So next is the Kalman filter. So this Kalman filter here, it plays a major role, significant role. So because this Kalman filter is a motion-based tracking by predicting the new location of each track based on its previous state and also the state dynamics. So this is the output of that code. So finally, this pedestrian tracking system that can be integrated into the various applications. So the main application is the autonomous vehicle applications, or other than this, surveillance systems or crowd monitoring. So this pedestrian tracking from a moving camera, it involves a combination of this computer vision and machine learning and optimization technique to achieve the reliable and accurate results in a diverse scenario. So this is all about today's session. Thank you all.